turn the sound. Hello guys, my name is David Cruz.
My name is Victor Nguyen.
My name is Gabriel Enciso.
And my name is Ian Gonzalez, and we form Team7, and this is our project, Netflix and Chill with Mr. Cow. Let's begin. All right, so our motivation is that Mr. Cow wants to Netflix and chill. However, his current viewing position of his TV is not optimal for him to see his whole TV. To fix this problem, Mr. Cow wants to mount his TV to his wall so that he can watch TV more comfortably. In order to do this, he must find a mount that will fully support his TV. He found a product online, and using his knowledge from MAE157, he will confirm if the project is good through various analysis. This is our structure. It is a TV mount that can extend and retract through folding. There's a wall mount clamp with two parallel rectangular beams and a single beam that holds a thin plate that holds the TV. The wall mount has a range of 180 degrees of motion and can form an angle between two parallel beams and a singular one that holds the TV. The thin plate that holds the TV can also be angled up and down for glaring purposes as seen in the figure on the bottom right. And I'll pass it on to Gabe for the objective.
Thank you, Ian, for the very specific description. So the objective of our project is that we want to analyze the different mechanical stresses that affect the different types of loads on the TV stand, as well as the different types of loads and fixtures that applied to the mount. We will be doing three different analysis on this: structural analysis, failure criteria, and minimum mass design. For our structural analysis, we will analyze the static forces needed in order to keep the TV on the mount. So this means that we will analyze the free body diagram that is being affected, or that is affecting the mount. And for failure criteria, we will figure out what will cause the mount to break by testing out the factor of safety necessary for a product. So this means that testing out the best possible dimensions, specifically the base. And for our minimum mass design, we want to get the failure criteria for yield by analyzing the material of the mount. So our standard material that is being shown as an example for presentation is a carbon steel, but we will also be testing for aluminum alloy and stainless steel. So for our structural analysis, we will be treating we are breaking apart the structure into three beams and treating it as cantilever beams. For our beam one, which will hold the load of the television, we are applying a downward force, signifies the weight of the TV, and we'll be analyzing the free body. This is the free body diagram of that. For beam number 2 and beam number 3, we will be splitting the downward force into two, as shown in the downward forces right here, and also adding in axial forces for beam 2 and beam 3 to signify when the TV is at a tilt, so that the force is at an angle and causing the axial strain.
So for our failure criteria, we need to look at the moment stress that's induced by the weight of the TV. As shown in beam 1, we modeled the beam as a cantilever beam, and we can then break it down into reaction forces. As shown in beam 1, we can see that there are both vertical and horizontal reactionary forces and a moment produced at the base. We can then use our equilibrium equations to solve for these reactionary forces. Since there is no axial load on the beam, we can then induce that there's no reactionary horizontal force. For a vertical force, we know that the reactionary force will be equal to the weight. Since the weight's at a length from the beam, we know that moments produced going downwards or clockwise And then we can induce that the reaction moment produced is the length of the beam times the weight. We can then use our beam stress criterion to solve for the minimum mass and width of the beam. First, we look at our strain, which is given in both the axial, XY, and XZ plane, and then as well as the stiffness matrix or stiffness of the beam. Since the beam is deflecting downwards, we know that the stiffness is negative, as shown as KY is less than 0. So since there's no axial and bending in the XZ plane, we know that strain in the axial and strain in XZ is 0. So then we can deduce that the strain is only a function of the Y plane. Using the equation of stress, we could then solve for the integral of the moment of Y. And then we get that the moment Y is a function of KY, the Young's modulus, and the moment of inertia of the beam, which is given as base times height cubed over 12. We can then solve for the minimum mass and the width in the next slide. So we can then induce that the maximum stress is at the base or top or bottom of the beam. So earlier in the equation, we had that the stress is a function of Y, and we plugged in height over 2 in terms of the Y, so to find the maximum stress. And then we know that the stress criteria is that the factor of safety times the maximum stress must be less than the yield stress of the material. And then we can just plug it in and solve for the minimum base and minimum mass of our beam. And then we know that the moment of Y is a function of the weight and the length of the beam. And thus we have the final equations of minimum mass. And as you can see from this table, that we have our 3 different materials that we'll be looking at. In particular, we're looking at the density and the yield stress, or the yield strength of each material. Yeah.
All right. For our results, we knew that the total TV extension length was around 14.5 inches. So each beam 1 through 3 had to be around the same length of 7.25 inches and have a height. And we set the height to 25 millimeters. Looking up the average TV weight, we found it to be around 50 pounds. We assumed a factor of safety of 2, considering standard loading and reliable material. In this case, we're assuming that the material is carbon steel. And after those assumptions, we found our minimum mass and minimum base length, which was for minimum mass was 0.168 pounds, and for base 0.069 inches. So in conclusion, the TV mount structure can be simplified into 3 cantilever beam supports with clamps at the end. For failure criteria and minimum mass, we can use known material properties and constraints of TV length extension to solve for the dimensions of the beam and total mass. So after all that, we can ensure that Mr. Cow is safe to watch Attack on Titans with his friends.
Thank you.
Thank you.
Thank you.
Thank you.